Uh, Good evening. So we'll be starting the class in a minute or so. Just waiting to see if anyone is joining, and then I'll start the class. So yeah, we can go for a brief recap of the previous class and then continue with today's class. So initially we saw what electrode is, what electrolyte is, um, the electrolyte interface, then why we need a supporting electrolyte, and how we are setting up the experiment. And that we saw the need for the reference electrode, the need for counter electrode, what reference electrode is, what counter electrode is, what is working electrode. And then we also saw how we are expressing rate constant, like how is it related to the potential. Then we slowly moved to impedance. In impedance, we are before that we see how potential versus current relation is. Then we see what is impedance. Then we see phase, magnitude, impedance, etc. So here, first we started with the electrode electrolyte interface, where we see that the ions from the solution come and gets absorbed on the surface of the electrode. So there is a charge distribution happening. So one type of ions from the electrode also come towards the edge where it shares with the electrolyte. So we have charges of different polarity aligning itself, forming the inner Helmholtz plane and the outer Helmholtz plane, and these ions are also solvated. So we see that when the starch separation is happening across the boundary of 1 nanometer, we say it's a Helmholtz model, and we see that it's just 1 nanometer where they are applying. If we apply 1 volt, there will be some electric field of so high, 1 gigawatt per meter. Then we went to Bowie-Chapman model. And Bowie-Chapman model, we see that no, it is not a, I mean, charge separation happens across a much larger area, and that is 10 nanometers. So we say that when the electrolyte is very concentrated, like 1 molar solution and all the charge separation can happen near the electrolyte interface. And we say that this following a Helmholtz model. And if it is solution of a lower concentration, like 1 millimolar, we say that Bowie-Chapman model is better. Then Stern model is something that combines the IHP, OHP, and Bowie-Chapman model, and it says most of the charges line up next to the electrode, but some of them get distributed across the electrolyte. That's about the Stern model. Then we saw that the stars lining up. So basically, that's the charge separation and it's getting lined up. So there is no movement of material which is happening, but just a charge separation happening, which we are saying it's a double layer capacitance. So here no reaction is happening. Now at the same electrolyte interface, if I apply some potential, what is happening? Because the potential is applied, we say that a reaction will happen and there is a current involved. We say it's an electrochemical reaction. Electro because electron transfer happens, and chemical because of voltage. Because of the application of the voltage, we see a current drop across, current developed across the electrolyte interface. Then what is impedance? When we are applying some potential, there is an electrochemical reaction happening, and this gives rise to current. And because of this current, there is a resistance developed, and we say that that's what is impedance. So for an electrochemical reaction, that is where there is electron as well as chemical reaction happening. Electron transfer also happening. We say that the impedance associated is called Faraday impedance because it's something associated with some reaction. Now, when there is no reaction happening at the electrode electrolyte interface and simply charge lineup happens, we say that it's double layer capacitance. Now, for instance, if we see that there is a metal dissolution of something happening, apart from the charge separation happening at the electrolyte interface, because of the double layer, we also have some impedance or occurring, and that is represented in parallel to the double layer capacitance. Now, two electrode setup, we will have double layer capacitance and a Faraday impedance in parallel for two electrodes. That is one for M and one for N. And besides that, there will be some drop in potential across the electrolyte because the resistance is offered by the electrolyte. So that is represented by solution resistance. Now we saw that how to measure the impedance of or the how to measure the electrode potential. When a so we want to measure the potential of an electrode which is immersed in an electrolyte. So we can use a multimeter in order to measure the potential. But what is happening when we are one of the knob is connected to the electrode and the other knob is simply immersed into the electrolyte. But that knob also develops a potential or charge separation in the electrolyte. So we cannot measure the potential of the electrode alone, but it is always measured with respect to something. So if in this case it becomes x minus y. So now we want to measure the potential of our working electrode, the electrode of our choice. And if I'm applying, if this one is the working electrode X, and I'm applying 1 volt, some voltage is taken up by this and some by this. But we do not know how much is taken up by our electrode and how much is taken up by the other one. Now, if I increase the voltage also, it doesn't mean there is a proportional increase in both the electrodes. It can be anything, 1.1 here, 1.1 here, and minus zero point 0.4 or zero point 0.9 and minus zero point 0.6 or anything. So it is not possible to say. So we want to measure the potential of our electrode of our choice. So we are going to measure report that with respect to the electrolyte. So we need to measure this accurately. So this can be done only if the potential is reported with respect to another electrode whose potential is not changing in any situation. That is what it is non-polarizable. Whatever potential I apply, its potential should not change. So that which whatever increase in the potential is seen, I can say that it's because of our working electrode. That is where the reference electrode comes into play. And we also see that in order to, when we are applying the potential, there can be some drop in potential in the electrolyte. In order to minimize that, we have to have the reference electrode close to the working electrode. So sometimes the reference electrode cannot be kept very close to the electrolyte. Sorry, the working electrode. So in that case, we make use of a lugging capillary. This is done so as to minimize this solution resistance between the reference electrode and the working electrode. Then we saw the case of different reference electrode like Ag bar AgCl, polymer electrode, standard hydrogen electrode. So we say that when we have reference electrode connected to the working electrode, it will have one that is ZF parallel to the double capacitance and R solution. We usually say that the reference electrode offers very few, very negligible resistance. Then we told we are when you're passing some potential, when you're passing some current, the potential is developed across both the electrodes, right? So, if large current is passed, this current passes through the reference electrode, it can damage the reference electrode. Then we cannot say that it's non-polarizable. So, what can we do? We can introduce another electrode to the system, which is called the counter electrode. So, what exactly happens is the current is passing from reference to, current is passing between the working and this counter electrode, and the potential of the working electrode is measured with respect to reference electrode. So the idea of introducing counter electrode is that for any reaction that is happening in working electrode, some alternative or the counter reaction should happen so as to complete the circle. So that can happen in the counter electrode so that no current passes through the reference electrode and we maintain the condition that the reference electrode is non-polarizable. So there we sell the counter electrode or the auxiliary electrode. Then we have both the complex voltage and applied voltage. The applied voltage is that is working electrode voltage minus reference electrode voltage, and the complex voltage is working electrode minus the complex voltage. Sorry, counter electrode voltage. Now, what can we use as a counter electrode? We usually go for a PT wire, or it is better to go for a mesh. Why we need to have a large area? Why whenever we are changing a voltage at the working electrode, that effect is also seen in the counter electrode. Suppose large current density is applied at the working electrode and large current is passing through. The same amount and some potential is seen in the working electrode. In order to maintain this potential at the working electrode, the current is getting applied also at the counter electrode. The current can be very large sometimes. So if the area of the counter electrode is very small, the current per unit area is going to be very large. So this current is supplied by the potentiostat. So sometimes that is higher, that becomes very much higher than that of the limit to which the potentiostat can supply current. What happens if we are actually going at a very harsh current means we are abusing the equipment. So in order to minimize the current at the cathode side, In order to minimize the current at the counter electrode, we can go for a mesh-like system where the area increases and thereby the current per unit area reduces, and we are operating well below the compliance, the current limit. Okay. And then we saw why we are adding supporting electrolyte into the system. So supporting electrolyte increases the conductivity of the electrolyte without changing the system. So thereby we can increase the conductivity and thereby reduce the potential drop at the electrolyte interface. So example is sodium perchlorate. Yeah, then we saw when an electrode is immersed in a solution, the reacting species are coming from the bulk and they come to the electrode, they react at the electrode interface and the product have to move out. So when we are applying small potential, the rate of the reaction is very small and we have enough reactants to come to the surface and react. So in this case, it is kinetically controlled. But what if the rate of the reaction is very large because the potential we applied is very large? In this case, the molecule we are conducting the reaction at a very high rate. The molecules might not be able to come to the heteroelectrolyte interface at the same rate and react. So this is called because so there is a mass transfer limitation or a diffusion control. Yes, so that were the two cases we saw. Then we saw how to change how does potential change the rate constant. So basically, some amount of potential is applied. That entire potential is not. It will help to change the activation energy of the reaction and thereby help to conduct the reaction at a much smaller energy level. Yes. Then we came to the impedance. So last class we stopped with impedance. We conduct we I went through it very fast, so I'll be starting from here. So impedance, first one we saw was resistor where the current and potential are both in phase. So the current value does not change with frequency and we found that the resistor value is EAC naught by IAC naught and there is no phase, both are in phase with each. So the both current and potential are in phase with each other. Then we saw the capacitor. So in capacitor, current is leading the potential by 90 degree. So this means even when the current is starting, the current I have given by uh, single line and current by the dash line. Even when the current potential is zero, the current has already reached a value. So the current is leading the potential. When in this case, when frequency increases, the current is also increasing. And here IAC equal to C dE by dt. So when we are differentiating, we get C omega EAC naught cos omega t, C omega EAC naught sin omega t plus pi by 2. Pi by 2 because current is leading. So here I can say the value, the omega, what to say, in this case, EAC naught by IAC naught equal to EAC naught by C omega EAC naught is equal to 1 by C omega. Now, here the negative sign here, okay. Now, when it comes to the phase becomes how much? EAC is the potential we are giving, that is in our control. So, we say it is at phase 0. And here the current is at a phase of pi by 2, it's leading. So, 0 minus pi by 2, it is minus 90 degree. So the impedance is minus 90 degree. So the phase for a capacitor is negative. The phase for the impedance of a capacitor is negative 90 degree. So that's why. So 1 by C omega. So one more point to add over here is for higher frequency, it will be easy. For higher frequency, it will be easy to pass through a capacitor, and for a smaller frequency, it will give up by zero frequency, meaning here this is going to be zero. So omega is going to zero. This entire term is going to be infinity. So it is going to be very, what to say, it is going to offer infinite resistance. Now in inductor, we say current is lagging by 90 degree. When omega increases, current is reducing. So same way L di by dt, we are differentiating the current and we get this is L omega I is equal sin omega t plus pi by 2, right? Now, yeah. So, yes, now after this, we are just going to see about, just give me a moment. Yeah. So here, the impedance value will be J omega L. So, and here the impedance is going to have 90 plus 90 degree because we have the current which is lacking the potential by 90 degree. Yes, so now we also saw impedance as a magnitude and a phase. Magnitude is nothing but EAC naught by IAC naught can vary from 0 to any value, and phase can be phase of the potential minus phase of the current. Phase of the potential is usually 0 because that is in our choice. 0 minus the phase of the current, and this can vary between 0 to 360 degree. Yes. Now, so this way we stopped. We said j omega L current lag, so it is 90 degree. We were now, as I mentioned in the last class, we'll be starting with some problems so that we'll get to know. Yes. So in this class, we're going to see series parallel connection, the graphical representation, types of analysis, sign, single sign, multi-sign, harmonics, stress factor, and windowing. So these are the topics that we intend to cover today. Yeah. One more thing that we have to say before proceeding to this is that this is where we stop. Now we're going to see the next portion, and that be in impedance. In impedance, what we are actually doing is we have an AC superimposed on DC. Okay, and in something that we need to understand is that in impedance we are not measuring V by I. Instead, what we are measuring is differential impedance, which is nothing but dE by dI. And why this is important is there can be systems in which we are applying a potential. So current, this is the potential versus current plot. Though when you are increasing the potential, the current can increase and after a point can decrease. Decreasing here means that can be due to some passivation or something. When you are applying high potential, the passivation is growing and sometimes the current reduces. So here current reduces. Okay, the current here reduces doesn't mean that it is being negative, instead it's meaning that it is lowering. So as I mentioned, what we are going to take in impedance is the differential impedance and not the V by I. So in this point, let's consider 2 points. One point here, 1 point here, and 1 point here. So in this point, if I take the value, the first thing to understand is at any point, E by I is not going to be equal to dE by dI. Okay? Because one is going to be the slope and the other one is going to be the value, instantaneous value at that particular point. Now, in this point, dE by dI is going to be a positive value. Now, if I'm going to this point part, what happens? The E by I is going to be positive. But will D by what D by Di? It's going to be negative value because the slope of that point is negative. But so the point of explaining this here is that there are times when we do impedance, we actually get the impedance to be negative. So a question shouldn't arise like how is the impedance going to be negative? We already know we have applied some DC bias which is positive. So if it is in terms of E by I, and if I say I have applied a positive potential and your impedance is negative, it gives a feeling like the current is negative. But current cannot be negative, or current negative means the direction of current is changing. But in actual case, that doesn't have a physical meaning, because the current can always flow from higher potential to lower potential, and a negative current means a change in the direction, which is not going to happen in the system. So the point here to understand is, when we get impedance as negative, the meaning is that the differential impedance is negative, which is because we are seeing a drop in the current when the potential is increasing. So one shouldn't think that the direction is reversed. That's why we are getting an impedance to be negative value. So that's about that. Now the next thing we have to understand is impedance. We usually notate using Z, and we also have admittance, which is Y. Okay, and it is what to say, inverse of the impedance. So when we are doing calculation, we can use either in impedance or in admittance form to do the calculation, depends upon the easiness. So now let's start with the series parallel connection. Let's go to the next page. So in this, first we have to look into Kirchhoff's law. So what does Kirchhoff's law say? At any junction, whatever current you pass through, it should come out. Okay, so that is current flow in equal to current flow out. So this means also means algebraic sum of voltage in any loop equal to 0. So why this? These are the rules that we are going to use when we are going to solve it. The first one being, this is kind of easy. So here, the impedance is going to be, the two of them are in series. So we are going to add up sum of resistance. So that is R1 plus R2. Now what if they are in parallel? So we have Z 1 by Z equal to, or Y, which is admittance, equal to 1 by R1 plus 1 by R2, and that is R2 plus R1 by R1 R2, and Z equal to R1 R2 by R1 plus R2. Now these are simple cases where you just have two resistors in parallel or series. Okay. Now let us move on to a much complex system. Complex system means where we have both resistors and parallel combinations. So let the first one be, we have one R and one C. How do we do it? Yeah. So what is an impedance of a single resistor? Impedance of a single resistor is equal to R. Now what about a capacitor? That is nothing but 1 by j omega C. So because both of them are in parallel, we know that the sum of impedances ZR plus ZC, and that is nothing but R plus 1 by j omega C. Okay, this was an easy case. Now what about, so um, what about uh, one resistor and one capacitor in parallel to each other? So 1 by Z equal to 1 by ZR plus 1 by ZC, right? That is 1 by R plus 1 by j omega C. So that is nothing but 1 plus j omega C R. R. So Z equal to R by 1 plus j omega C R. So this is how we can do for when they are in parallel to each other. Now the next question is, can I use differential uh, equation? So here presently we have used equations where we are using a frequency response, how based on omega. Now how can I use a differential equation to find the impedance for the same system? Let's take, so this was the easy way of doing, but let's look into how to use differential equation in order to find this. You have R and C. So for the same case, how can we arrive at this equation if we are have using differential equation? So the current comes here, some part of current goes here, and some part of current comes here. Right? That's based on the Kirchhoff law. When there are two, they are in parallel, you have some amount of current going here and some amount of current going this way. So I1, and when they are in parallel, the potential is same. So I1 equal to E by R. And what about I2? That is nothing but C dE by dt. So I1 equal to EAC naught sine omega t by R, right? Because E equal to EAC naught sine omega t. Similarly, I2 equal to C. Now if I differentiate it, EAC naught omega cos omega t, right? So this is how you'll get I1 and I2. Now I total equal to I1 plus I2 equal to EAC naught sine omega t by R plus C omega cos omega t. Yeah, this is the equation we get. So now if we are trying to plot this, so I give some values for EAC naught and omega naught. That means if I give the range of frequency, if you're plotting this, you have the equation for the current and EAC, you can find the impedance. Okay. So this is how the I total. So this is how current is related to this how the equation will be if it is a time domain related. Okay. Now let us do some calculation. Uh, so for a given R and C value, if I am giving it as a function of what to say omega. So in this case, this is the value of impedance that you're going to get. Okay, if I am going to plot this as a function of omega, you'll get a plot. Similarly here, if I do so this IT, so now we also know Z equal to EAC by IT. Okay, so I am again going to plot for the given value of R and C. If I get plot this as a function of omega, you will see that the response is going to be similar as in the previous case. Now, let's do a problem. R equal to 1 ohm, C equal to 0.01 farad. It has a sinusoidal wave and has a frequency of 10 hertz. Now you will have to find out the impedance, you will have to find out the phase, you have to find out the magnitude. There's a question. How will you do it? How will you do it? So the first one is omega. So omega is nothing but this 2 pi f. So 2 into 3.14 into frequency value is 10. You get 62.8 radians per second. So you can try with you can use your calculator and find the value. I've already solved it. I'll be showing you how you get this. Now, what about impedance? So we are going to take the case where a resistor, sorry, I haven't given the figure. There is R and capacitor in parallel R. and capacitor in parallel. So what is going to be the impedance? You have both resistor and capacitor in parallel. So how is the impedance going to be? The impedance is going to be the sum, right? R plus 1 by j omega c. So nothing but R value is 1 ohm, and then capacitor j omega is 62.8, and c value is 0.01 farad. So if I solve this, so 1 by j, I can multiply with j on both the sides. I'll get j by minus 1, because j square is minus 1. J is root of minus 1. This is nothing but minus j. 1 minus j by 0.628. And if I solve it, I get 1 minus 1.59 j. This is the impedance value that I want to get. Any doubt till this? I hope this is clear to everyone. Now from this, I have to find out the magnitude. I'll do it here itself. Magnitude is going to be the root of square of the real value plus the imaginary value, which is 1 square plus 1.59 square. And that is root of 1 plus 2.5281, and that is 1.88. Now same way, the phase is going to be tan inverse of minus 1.59 by 1, which is minus 57.8 radian per second. So if you have the values for the resistance, capacitor, inductor, this is the way you have to follow. This is the steps you have to follow in order to find the magnitude and the phase. Now, instead of capacitor, if it was an inductor, the only difference would be here. Here, instead of 1 by j omega c, if it was inductor in parallel to a resistor, it would have been resistor's value plus j omega l. And the rest of the values, the steps would continue. You need to have the value for inductance, right? I hope this clear. Okay. Now the next one is graphical representation. So let me say I have a circuit like this. This R1, this C1, this is R2. Okay. So this is called a simple random circuit. Okay. Here, this is a simple random circuit, and in this case, the R1, okay, R1 here is called the solution resistance. So when an electrode is immersed in an electrolyte, there is some drop in potential in the electrolyte interface. We say that there is a resistance offered by the electrolyte, and that is solution resistance, and that is given by R1. Now, whenever we have a capacitor in parallel to the resistor, here some reaction is happening. I said whenever an electrode is immersed in an electrolyte, the electrode forms a double layer with if there is a double layer formation at the electrode electrolyte interface because of the charge separation. This is called the double layer capacitance. So any electrode with a immersed, that happens. So we always have a double layer capacitance. Besides, if there is any reaction happening, it is always, so that if you remember, it was Faraday impedance, and we said it's always in parallel to the double layer capacitance. In this case, I am representing a Faraday reaction by a simple resistor, which is R2. So this portion corresponds to any reaction which is happening in the system. Okay. Now, if I have to find the what to say the net impedance of this entire circuit, how will I do it? So here I know C1, the capacitor and the resistor, they are in parallel to each other. So first I'll have to solve this. So when two are in parallel, it's always useful to go for admittance because we simply have to add it. Because in impedance, it is always in, we have to take the reciprocal, right? When they're in parallel. So when the two things are in parallel, it's always useful to go for admittance and then convert it to impedance. And then similarly, when this entire system is in parallel to the single resistance, so there we can add it up. So let's see an example. This is the example. How will we solve it? We have a resistor which is in series to a capacitor and a resistor which are connected parallel to each other. I think questions of this kind are there in the assignments. Even the week one assignment, I think the 4th of February is the last day to submit. So I think this part is going to be useful to you. So how do we solve it? The net impedance of this is going to be, let me take, in this region. First, let me say this is R1. For listeners, this is R1, C1, R2. Both in this region, they are in parallel. C1 and R2 are in parallel. So here, let me say Z parallel. Because they are in parallel, I am going to use the reciprocal. And that is 1 by R2 plus 1 by J omega C1. Right? So if I am writing this, it becomes 1 by R2 plus J omega C1. So just taking the reciprocal and finding the impedance, it becomes what? 1 by R2 plus 1 by J omega C1. Okay. Now if I substitute the value, it is going to be 1 by 100 plus 1 by, sorry, I made a mistake. It's not 1 by R2 plus J omega C1. And here it is J omega C1 value is 10 to into microfarad. So microfarad means 10 to the power minus 6. So this is going to be the impedance of the Z parallel. Now what is Z total? You have both in parallel. That is R1 plus Z parallel. So R1 is nothing but 20. So this value is going to be 1 by J omega 10 to the power minus 5 plus 1 by 100. Now what I'm going to do is, because it's 1 by 100, I'll just multiply the denominator and numerator by 100. Let me do this in next page. I'll write this down again. Z total equal to 20 plus 1 by J omega 10 into 10 to the power minus 6 plus 1 by 100. Now I'm going to multiply everything by 100. That is 20 plus 100 J omega 100 into 10 into 10 to the power minus 6 is 10 to the power minus 3 and this becomes 1. Now, what is this in the form? This is A plus B. So how do you actually normalize? So I want to remove this j from here. What can I do? I can multiply by the conjugate in the numerator and denominator. How do I do it? 20 plus 1 plus 10 to the power minus 3 j omega 1 minus 10 to the power minus 3 j omega 1 minus 10 to the power minus 3 j omega. And this is nothing but 20 plus 1 minus 10 to the power minus 3 j omega by a plus b into a minus b, a square minus b square. So this is 1 minus, what about here? J square omega square 10 to the power minus 6. J square is again negative 1. So I can make 1 minus of minus, which is 1 plus 20 plus, uh, I forgot to write the 100 which is over here. Yeah. 100 1 minus 10 to the power minus 3 j omega by 1 plus omega square 10 to the power minus 6. Now, let us split this into real part and the imaginary part, which is 20 plus 100 into 1 by 1 minus omega square 10 to the power minus 6. And I have another term, 100 into minus of 10 to the power minus 3 j omega, which is 100 into 10 to the power minus 3 j omega 1 minus omega square 10 to the power minus 6. Okay. So here the real part is 20 plus 100 1 minus omega square 10 to the power minus 6 minus j 10 to the power minus 1 omega 1 minus omega square into 10 to the power minus 6. So this is going to be real part and this is going to be imaginary part. Now, if I'm going to plot this, what can I get? If you're going to plot this using Impedance, I mean using a software, MATLAB software or something, for different value for omega varying from 100 kilohertz to zero point 0.1 hertz or something, you will get a curve like this. So this one corresponds to high frequency regime and this one corresponds to low frequency and this one I can say it is a mid frequency region. But now my question is, can I guess what the value, this value is or this value is without actually solving this? Is it possible? The answer is yes. And how? Let us see. So, this is 20 ohms. This is a capacitor and this is again a resistor. Okay. Now, what is happening at a high frequency and a low frequency region? High frequency and low frequency. So the current is going through this. Now it has either option to go through this way or this way. Now we know that there are 1 by j omega c is that of the capacitor and the other one has a resistor R for any value. Now what happens at high frequency? High frequency means omega tends to infinity. What happens to the capacitor value? 1 by j infinity c with the 0 and R will remain the same. So here, okay, now what happens at low frequency regime? Low frequency, omega tends to 0. Capacitor value is 1 by j into 0 into c equal to infinity and R will still remain. R value doesn't change with frequency. Now, you have current passing through this way. Okay. Now it can either go this way or this way. The whichever way it goes, it will be always trying to take the path where the resistance is the least. Now let us again come. So the least resistance is what it will, least resistance or impedance is what it will be looking at. Now at high frequency regime, when omega tends to infinity, capacitance offers a resistance of 0 and R will still have the value. So out of this, which has the lowest resistance? This is what is having the least resistance. So when we are actually going through what to say, when we are going through the circuit, how will it go? It will follow this path. It will go through 20 and then it will take this path, right? This wouldn't have any effect. So what is the net total impedance here? So there is a resistance R1 which is 20 plus this one which the capacitance offers very low resistance value of 0. It's 20 ohms. So when we look at this plot, okay, we said that when we are plotting this one, we will get a semicircle. So this one is high frequency, this is low frequency. So what is the value at high frequency? This is 20, right? So this value becomes 20. Now, what happens at low frequency? Low frequency omega tends to 0, capacitance is offering infinite resistance. Now, it has a tendency to go through the path where the resistance is least. It will go through the resistor, it will go through the resistor, and then this will go through this way because capacitor is offering very high resistance. So, what is the value? So, for this question, which we had done, the value of the resistance is 100 ohm. This 100 is 20, and this is 10 microfarad. So, this 20, this is 100, and this 20 microfarad, 10 microfarad. Okay, so now what is the resistance? Z equal to 20 plus what is the next resistance? 100. That's 120 ohms. So at low frequency regime, when omega tends to very small value of 0, mean close to 0, the net impedance value is 120. So this value is 120. So in this way, we are able to guess or understand for a small circuits like this, we can predict what will be the starting and the end value without actually doing the calculation. And this is one example. So is this clear? I hope it is clear. Now we have different plots. One is Nyquist plot. In Nyquist plot, we'll be plotting minus z imaginary versus z real. Okay, minus z imaginary versus z real. Okay, and the next one is body plot. The shape it depends upon which all elements can be rested, capacitor, etc. In body, we face plot minus phase versus frequency and magnitude of the impedance versus frequency. We also have a 3D plot where we plot z real and minus z imaginary versus frequency. So these are the different plots which are used in impedance in order to represent data visualization. These are the different plots. So with this, we come to like the week one classes have the contents of what to say the week the assignment contents for the first week has been concluded. So this portion was went pending last week, but this became important because we can expect questions from this portion in the consequent assignments. Now let us move on to the next. So finals will be discussed only after we are the last date for the experiments are done with. Okay, we will be then discussing the experiments. Just give me a moment. Now in week 2, the next portion is the type of analyzer. And then we'll be also looking into sign and multi-sign waves. Okay. Now the experiment. So in order to do the impedance experiment, we require a potentiostat, potentiostat, potentiostat or a galvanostat. Both can help us to measure the impedance. Okay. Or we also need a frequency response analyzer plus either one of this, potentiostat or galvanostat. Now, the range of frequency in which the experiment is done when we are procuring the equipment can be from 100 kilohertz to as low as 10 microhertz. So most of the data we will be getting from the mid frequency regime, like up to zero point 0.1 hertz or 0.001 hertz and all. So do we need to actually go to higher frequency? No, this limit is more than enough. But in some, there are equipments who can provide up to 32 megahertz, and the 32 megahertz it's usually used for liquid-based system. But for other systems, we actually do not need such a high frequency. It is enough to start from 100 kilohertz to, because when the frequency is the upper limit is very high, the lower limit can become low. So I mean, it can be won't be that low. So in order to cover the entire range, it will be ideal to have from 100 kilohertz to up to 0.001 hertz, etc. So when the frequency is reducing, when we are going to the lower frequency regime, we know that the period is inversely proportional to frequency. So when frequency is reducing, the time taken to get the data or a cycle, that is increasing. Okay. So and the problem is data can be noisy at low frequency, because also because it's taking so much time. This is a overall introduction into this topic. Now let us see the types of analyzer. So in the type of analyzer, the first one is oscilloscope. So what is happening in oscilloscope is at a given frequency, we are applying a sinusoidal wave. Sinusoidal potential. Now, when the potential is applied, we'll get the current response. Now we'll plot potential versus current as a function of time. Time period. This is nothing but it is the inverse of the frequency. So we'll apply frequency, we'll get a sinusoidal potential. We are applying a sinusoidal potential and we'll measure the current response. Then this potential versus current is measured reported as a function of as a function of the period. Now this also helps us to understand if response is linear. Then, based on this data, so there's a point around which the potential and time is measured. We take a printout and then we manually calculate the impedance. This method is not used nowadays. Okay, so this is about the oscilloscope. The next one becomes lock and amplifier. So in lock and amplifier, we use a technique called cross correlation technique. It's important to know the name of this technique. Now the third one is fast Fourier transform FFT analyzer. This FFT analyzer. We also have something which is called response frequency response analyzer. In most of the cases, this is an FFT, but sometimes it's also cross correlation. It uses cross correlation technique. Equipment uses cross correlation technique and calls it FRM. So you should know which are the different waters to analyze. The first one is oscilloscope, which is manually done and it's not used nowadays. Then beside that we have lock and amplifier, which uses cross correlation technique. Then we have the FFT, fast Fourier transform, and then frequency response analyzer, which can be either fast Fourier transform or a cross correlation technique. In either case, it can be called as the equipment can use any of them, and they're calling it as frequency response analyzer. Now, the next question is, in which mode can we run impedance? So this is an important question. So what is happening in impedance is we have a DC bias and we are overlapping it with a small AC bias. And so basically it is more or less that DC bias value, but it is actually oscillating around it. So we say it is kind of, so system is not disturbed from the equilibrium, it goes slightly here and then comes back and then we're taking the response. So the DC bias superimposed by AC bias. So this DC and AC bias, it can be either in current mode or in a potential mode. Either DC potential can be overlapped by a potential bias, or it can be an DC current which is overlapped by an AC current. So it can be running either in a potentiostatic or a galvanostatic mode. So potentiostatic means we are having a DC potential which is overlapped by a small, over which we give a small AC potential. Galvanostatic meaning small AC current over which we are giving DC current over which we are giving an AC current. In either case, it is not constant potential or constant current because it varies a little, right? Potentiostatic actually means constant potential. But is that the case here? No. We have a DC potential which is superimposed by an AC potential. So it varies a little from the DC potential, comes back. Again varies, comes back. But that variation is minor. So more or less it is a constant. So that's why we use the term pseudo potentiostatic and pseudo galvanostatic and not potentiostatic or galvanostatic. So the potential this technique they are used in corrosion, biosensor, and deposition techniques. And this one in batteries fuel cells, etc. So this is about um, what to say, the modes in which we can run the experiment. Now, why we go for pseudo galvanostatic technique for batteries and not pseudo potentiostatic? Is there a particular reason for these energy storage material, energy storage or energy devices? Energy devices. Why do we go for galvanostatic and not pseudo potentiostatic? So again, let me take the example of battery. Impedance value is very low. It will be in milliohms region. Okay, it's going to be very low. So now, let me give you an example where I'm applying a DC potential of 10 millivolt. Let me take the case where I'm saying, oh, I'm going to run battery in pseudo potential static mode. And I say I'm going to give a DC potential of 10 millivolt. And we already know that the impedance value for a battery is going to be very small. So, for example, let me say the resist impedance value is 0.001 ohm, for example. So, uh, now what is going to be the output response? So, we know the Di will be nothing but VE by Z. This is going to be the output response in order of the current. So, 10 millivolt. So, it is 10 amp. See the current, although the potential you have applied is very small, because the resistance or the impedance value is very small, the output current is very large. So this has to be, I mean, so the current response is very large. So which is beyond the capability of the equipment. So it is a large current beyond capability of equipment. So you are actually damaging the equipment. So this was the case if I was going to do pseudo potential static mode. Now let me take the case where I'm going to do pseudo galvanostatic mode, where I'm going to give 10 milliamp current and imagine the resistance is impedance is going to be what to say 1 milli ohms. So what is the output potential going to be? V equal to Z into I. That is 10 into 10 to the power minus 3 into 10 to the power minus 3 ohm. Sorry. And in this case, your response is nothing but 10 to the 10 into 10 to the power minus 6 volt. The value is very small. This can be accurately measured by instrument. So this is why when we are doing experiment we use for any energy devices, we have to go for pseudo galvanostatic mode instead of a pseudo potentiostatic mode. I hope it is clear, right? Now let me again go to graphical representation. Do you remember how we used to get representation for a random circuit we had seen in the some time ago? So whenever we have a capacitor in parallel to the resistor, we'll get a semicircle. And we also saw the start value corresponds to this in value, and this value corresponds to, sorry, we also, and this value corresponds to the sum of this value, right? This is what we saw before. Now, what if, so for each resistor in parallel to capacitor, we'll see one semicircle. So what if I have two semicircle like this? Okay. This means we'll have two RC in series. RC means one resistor, one capacitor. They are balanced. Two RC in series will give me two semicircle. Now, what if I get something of this form? I have one resistor and one. There are two loops. The first loop over here and second loop here. So the first one, as we told before, one RC in parallel and one, if it goes to the negative, okay, I can say I can represent it by a inductive loop if needed, and further information will be provided in the later coming on classes. So, but idea here to say is that when you have a loop for going beneath and it's in negative imaginary, z imaginary value, then we can say so it's already negative of. Do not forget it is minus z imaginary versus z real. And if this value becomes negative, I mean, if it is going to this quadrant, we say it is an inductive loop which can be used. Now, we know we start at high frequency, we go to low frequency. This is high frequency, this is low frequency, this is mid frequency. Now, what if I get a inductive loop at the high frequency regime? This high frequency, this is low frequency. What if I get a, what to say, an inductive loop with the high frequency regime? So this happens because of multiple reasons. But this portion means this. But why an inductive loop happens at high frequency? High frequency means greater than 100 kilohertz. And now the first reason may be because of cables, instrumental artifacts. Because the equipment cannot distinguish whether it is coming from the system or from the cable. So equipment cannot identify where it is coming and it automatically gives the inductance. So how to overcome this? So in order to overcome this, we can use short cables. That the effect from the cables become negligible. Now the next reason is maybe due to distribution of current or potential. Maybe due to the distribution of current or potential is not uniform on working electrode. What does this mean? That is, there is no uniform distribution of current or potential on the working electrode. And this arises because of the size of the working electrode. That is, working electrode is very large, okay? But reference electrode is closed only to one part of the working electrode. Even in this case, we see that because the reference electrode is not very close to the working electrode, we don't get a uniform distribution of the potential and or current over the working electrode, and this also results uh, in the inductive value. So in this case, what we can do is take data at 30 kilohertz or lower value in order to avoid the inductive effect. Okay, now we are doing impedance. We get, what do we get from the impedance? Like impedance, what we get from the impedance means we have both the high frequency regime, we have low frequency regime, right? I say this is the circuit. I have high frequency, I have low frequency. So usually the high frequency regime, it gives information about the, this is very important. You can expect questions. Double layer capacitance. So the impedance arising from the double layer capacitance is provided in the high frequency regime. Low frequency, it talks about kinetics and mass transfer. So this is about what to say, the sine wave. Sorry, this is about what information we can get from the high frequency and the low frequency regime. So actually, if you want to know more about the reaction, we have to go to the lower frequency regime. Now let us start from single side. So single sign means we are applying only one, like at particular DC potential, we have to give some input, right? So that is single sine wave, and we get the output. Okay. So what we do, we are applying a single sine wave. We start from high frequency, we go to mid frequency, and finally to low frequency. Okay. We are setting. So this is the setting a limit to the. We can say what is the limit of the frequency. Usually we go from 100 kilohertz, and we can go as low as 0.001 hertz. So it all depends upon what range of frequency we are setting. So this is very important to decide which range of frequency we have to carry out the experiment. Now, we have set the limit. It is not that, so we know that the time period is inversely proportional to the frequency. We are going from 100 kilohertz to 0.001 hertz. When we are going to lower frequency, it will take more time. This means we cannot do, it is not like 100, then it is 999 kilohertz or like that. I mean, it should be, there should be some interval, I mean, at which the data is taken. So if I say 100 hertz, and I'm just giving an example. I can either go for 100 hertz and what to say, point 0.1 hertz if I'm going to take the experiment. Simply, I'm just giving an example. If I'm doing an example and I say total, so that means one more point hertz. That is 100 kilohertz or 0.001 hertz. I'm going to do the experiment. No, I cannot do it at each frequency. I have to give at what interval of frequency should I collect the data. So for that, I'm giving an example. Imagine I'm doing experiment from 100 kilohertz to zero point 0.1 hertz. And I say that between the total range of that frequency, I need to take data at 7 points. Now what happens? It will do 100 minus zero point 0.1. Okay. Between 100 and zero point 0.1, it will take any 7 points. Okay. It will take 7 equally spaced points. So it can be something like the first point is something. So how much it will be? 100 minus zero point 0.1, zero point 0.1 is negligible. 100 by 7 is, okay, for my easiness, I'm saying I'm going to take 10 points at which data is taken. So it becomes 100 minus zero point 0.1 by 10. So because it is zero point 0.1, I mean, it's negligible when compared to 100. So at every 10 hertz, it will take the data. Imagine that case. So although we are saying we're going to low frequency regime of zero point 0.1 hertz, for example, in this case, I'm not taking any data at zero point 0.1 hertz. My least point is 10 hertz. I'm not taking it 10. I'm not taking it 1. I'm not taking it, what to say, I'm not taking it 1 hertz. I'm not taking it zero point 0.5 hertz. I'm not taking it zero point 0.1 hertz. So am I really going to a low frequency regime if I say that these points are supposed to be linearly spaced? So this is the problem with, if I am linearly spacing the point, this is the disadvantage that I cannot cover the entire range of frequency. Then what can I do? So if I'm going from 100 kilohertz to zero point 0.001 hertz, I can say that within each decade means 10 to the power of what? So that is 100 kilohertz to 100,000 hertz. Sorry, from 100,000 hertz to how much it is? 10,000 hertz. And then it becomes 1000. Then it becomes 100. then it becomes 10, then it becomes 1, then it becomes zero point 0.1, then it becomes 0.01, then it becomes 0.001. What I can say is instead of linearly spacing, I can say within each decade means this is one decade, this is the next decade, okay? Within each decade, I need 7 points. How about this? We are covering more number of points in each interval. Compare with this. Here I am simply saying 100 hertz to 0.1 hertz, 7 or 10 points means it simply takes a linear spacing and I am not able to do it at lower frequency of zero point 0.1. Here when I am doing points per decade, within this interval I have 7 points, within this interval I have 7 points, like that. I'm able to cover data collection at every between each of the decades. So I'm going to get more evenly spaced out points. Okay, so it is always better to go for log spacing. This is called log spacing. Points per decade is better than linear spacing, especially if you have to learn about what is happening in the system at a low frequency regime. This helps us a lot. Now the next thing is amplitude. So the first thing we learned is to setting the limit of the frequency. The next one we looked is how to evenly space out those. Now the third one is amplitude. Amplitude also plays a very important role. So we have a DC bias. I am going to overlap it with the AC bias. So this is the amplitude, right? What? So it is something. It is oscillating. It can be this big. It can be this range, can be this part also. Which is better? Now, when I'm applying 5 millivolt, it doesn't mean it's going to be 5 millivolt. This itself will have some, what to say, noise. There's a noise also from the system. So, if it is this big, what happens is non-linearity is introduced in the system. We'll be seeing it later. It can be this one. Okay, now you see this one, very small. It is difficult to identify which is the amplitude because already there is noise, right? It is very small. So it is always better. We have a range of how much amplitude we have to give, which we'll be looking again. We'll come into this topic back again. So this is also important. Then the next thing is wavetime.